As far back as mankind goes, man has always tried to understand the environment that surrounds him. The unknown is scary. He was therefore undertaken to discover the meaning of life, the reason for our existence, our role on Earth. Life after death, meteorological phenomena, the birth of the Earth, or the creation of the universe. To understand the elements, to understand the hidden meaning of things, is a visceral need of man. This thirst for discovery drives us. For thousands of years, the Earth has been an eternal question for humanity. How was it born? Who is at the origin of its creation? What is it made of? What is happening in the universe? What is its role in the universe? What is happening inside the Earth? Our planet is exceptional, and for the moment at least, it is also the one and only planet where life is present. Our existence is only possible because the Earth admits all the essential criteria for life. The Earth is a vast subject that raises 1001 questions, but in this video, I propose to answer only one of them. What is the interior of our planet like? For that, I propose you a journey, an absolutely incredible experience, an adventure in which you are the hero with a capital H. You will become a geologist and go through all the layers of the Earth until you reach its core. The center of the Earth is our goal. You will board a capsule. This capsule is unique in its kind, capable of withstanding extreme heat and pressure. On board, you'll be able to defy the laws of nature and penetrate the deepest layers of our planet. You will be immersed in the bowels of the Earth in order to discover its secrets and its most complex mysteries. Because the Earth is connected to the Sun and the entire universe, you will also use a spaceship on your journey to experience the universe at its most beautiful and witness the birth of a star and a planet. Before leaving for a new adventure, think about liking the video and subscribing so you don't miss anything. Thank you all, and have a nice trip. If today, with the latest generations of telescopes, we can see very far, specialists estimate that we can only distinguish 10% of the matter in the universe. Can you imagine? What we perceive already seems immensely large, and yet it's only a tiny part of the entire universe. The remaining 90% is called dark matter, or hidden matter. And here, I'm not even talking about antimatter. Particles that have never been seen before seem to form it. Finally, we are all a small speck of dust in the universe. Let's go up there together in our galaxy. Let's travel a little in space to understand the environment in which the Earth gravitates and see how beautiful and impressive the universe is. Before going underground, let's get a little height on board our spaceship to discover a tiny part of the universe and our galaxy. The ascent is always impressive and a little destabilizing. Hang on. Here we are. We are stabilized. We are in space. Look how beautiful it is. You can see the stars, the planets, the galaxies. You can see a few, but scientists estimate that there are at least 2 trillion of them in the universe. The further we look into the universe, the more galaxies we see. A galaxy is a huge collection of dust, billions of stars and their star systems that revolve around a point. The whole thing is held together by gravity. If some galaxies exist alone, others are part of larger groups. They're called groups, clusters, and superclusters. This is the case of our galaxy, the Milky Way. The Milky Way is the galaxy where we are now. This view is extraordinary, isn't it? It is in this galaxy that our solar system has evolved since its birth. The Milky Way would have a size between 100 and 120,000 light years. Knowing that 1 light year represents 10,000 billion kilometers, I'll let you imagine the vast space where we are. In this infinite expanse, we share space with over 300 billion stars and 100 billion planets. The Milky Way is part of a larger group called the Local Group. This group extends over 10 million light years. The Andromeda galaxy is also part of it. But this is not the end. The Local Group, where the Milky Way and the Andromeda galaxy are located, is neighboring with the Virgo cluster, another set of galaxies. Together, they form the Virgo Supercluster. This concentration of galaxies is estimated by scientists to be more than 100 million light-years across. The Virgo Supercluster integrates another set, Laniakea, an even larger supercluster that has more than 100,000 galaxies. Such dimensions makes one dizzy, don't they? It is at this precise moment that we feel very small in front of the world that surrounds us. Before leaving, I let you admire the beauty of the universe. Time seems to stop. The lights dance. It is a true poetry which is played in space. Let's turn around before losing ourselves in this immensity. We will begin our descent from Laniakea, the Virgo Supercluster, the Local Group, the Milky Way, and then our solar system, to finally arrive near the Earth, our planet. Our project in this journey is to discover the depths of our planet, what it is composed of, and what are the phenomena that take place in the bowels of the Earth. But before that, we must define together an essential point. What is a planet? A vast question, isn't it? Not all scientists agree on the subject and the debate remains open today, but this will not prevent us from trying to find some answers. As we make technological advances, we also make progress in our discoveries. The new exoplanets, i.e. planets outside our solar system, show new characteristics and change our vision of planets. It must be said that they are sometimes far from the terrestrial neighborhood that we used to study until now. Even if the definition is complex, and that it is not always easy to put everyone in agreement, it was necessary to make choices. The International Astronomical Union has therefore decided. It has established basic criteria to define what a planet is and what it is not. To be named as such, here are the criteria that planets must meet. Criterion 1. It is in orbit around a star. Criterion 2. It does not share its orbit with other stars and celestial bodies. Criterion 3. Its mass is sufficient to meet the conditions of gravity necessary for it to be in hydrostatic equilibrium. Criterion 4. It has an almost spherical shape. Some astrologers also add that a planet does not shine by itself. It is the star that produces the light and illuminates the planet in question. The Earth meets all these criteria and is therefore indisputably part of the happy family of planets in the solar system, along with 7 other neighbors. These are Mercury, Venus, Mars, Jupiter, Saturn, Uranus, and Neptune. Pluto has been downgraded as a dwarf planet and is no longer considered a real planet for several decades. Astronomers discovered the Kuiper Belt some time ago. It turns out that Pluto is located beyond the orbit of Neptune, and that this orbit is composed of small icy bodies, of which Pluto would be part. It is simply larger than the other bodies. Have you noticed that our 8 planets are unique and at the same time very similar to each other? We could almost say that they form a family as we understand it in the human race. Each member has common genes, but each has its own characteristics that differentiate it from others. In astronomy, we consider 3 types of planets. It's important to know them in order to have all the knowledge necessary to study our Earth. For this, we will go back into space and approach Jupiter. You can't miss it. It is gigantic, and dozens of natural satellites orbit this planet. The gas giant planets are, as their name indicates, planets that are quite large, but not very dense. In fact, they're essentially made of gas. In this category, we find Jupiter, Saturn, Uranus, and finally Neptune. They are the largest in our solar system. They usually have several natural satellites orbiting around them. Jupiter has 79 satellites, including Ganymede, Io, and Europa. Saturn has 82 satellites, including Titan. 27 orbit Uranus, and finally Neptune has 14. That's a lot of people, isn't it? Other characteristics, they all have a thick atmosphere and a planetary ring, in the shape of a flat disk and composed of dust and other small particles, all orbiting a planet. If they are mainly composed of gas, according to the latest scientific studies, it could be that these gas giants contain a solid core in their center. You can see the planet Pluto through our super telescope. Do you remember it? It is a dwarf planet. Let's get closer and discover the characteristics of this particular type of planet. Recently created, you may not have heard much about dwarf planets. If they are indeed stars in the universe, they're placed between the planet and the small body. Before you get lost, here are a few details that will help you understand. Dwarf planets share some of the characteristics of the planets we know, but they also have some specificities that bring them closer to small bodies with particular properties. Dwarf planets share their orbit, i.e. their rotation path, subject to the laws of gravity and following a precise path with other stars. But you might tell me that the Moon and the Earth share the same orbit around the Sun, and that we do not consider it as a dwarf planet, but as a planet in its own right. Yes, that's true, you're absolutely right, but the Moon is a natural satellite of the Earth. However, this is not the case for dwarf planets. They share their orbit with other objects, mainly asteroids. These share their orbit with the dwarf planet, but it does not orbit the dwarf planet. Do you see the difference? There are 5 dwarf planets: Ceres, discovered in 1801, Pluto in 1930, Ares in 2003, Haumea in 2004, and finally Makemake in 2005. As you may have noticed, at least I hope so, the Earth has not been mentioned so far. So we'll turn back and go to our dear blue planet. It is indeed one of the Telluric planets, our last category of planet. To become a good geologist and enjoy your trip to the center of the Earth, you need to take some specific knowledge with you. Telluric planets have something special. This little something is one of the elements that allow us to live on Earth and enjoy its resources. Here are the specificities to know about this type of planet before leaving to discover the depths. What does the term Telluric planet mean? If I tell you that Telluric comes from the Latin word for soil, does that put you on the right track? These are planets essentially made up of rocks and metals, and which therefore have a solid surface, a soil in short. If we want to be more precise in the definition of Telluric planets, we must also add that they are made of solid rocks, and that they have different solid envelopes nested in each other. Now's the time to make your mind work, and to remember your years spent in school. Remember, there were 3 main layers: the crust, the mantle, and the core. In our system, 4 of our planets are considered as telluric. There is the Earth, of course, but also Mercury, Venus, and finally Mars. You may have noticed that these are also the 4 closest planets to the Sun. They're located just before the asteroid belt. To return to our rocky planets, here are some details to remember about each of them. Who knows, A general knowledge question about the planets might come at you like a meteorite during your next game of Trivial Pursuit, so take notes. It's your chance to show off your knowledge to your friends. Mercury is the closest to the Sun. To measure this distance, we speak in astronomical units. One astronomical unit represents the distance from the Earth to the Sun, which is about 150 million kilometers, or more than 93 million miles. Mercury is between 0.30 and 0.50 astronomical units, or AU, from the Sun. This is an average because the distance varies constantly. The Sun and the planets are in perpetual motion. To return to Mercury, it is also the smallest of our solar system. Indeed, it measures 3,474 kilometers in diameter, or about 2,100 miles, against 12,742 kilometers, or about 7,900 miles for the Earth. It takes only 82 days to go around the Sun. It also turns on itself 3 times, while it turns twice around the Sun. 1 day on Mercury is 2 months on Earth. If you were 42 years old, you would already be 2,519 years old on Mercury. Another particularity of this planet is that it has no natural satellite, like the Moon and the Earth, for example. It has no atmosphere either. Its temperatures are extremely variable, from negative 172 degrees Celsius to 427 degrees Celsius, i.e. from negative 277 degrees Fahrenheit to 800 degrees Fahrenheit. The day is hot and the nights are freezing. Water is an important element in the observation of planets for scientists and astrologers. We know today that Mercury has ice at the poles. Finally, on the far side, as you can see, Mercury is affected by many meteorite impacts. This explains the many craters that we find on its surface. Let's move a few astronomical units to approach Venus. It is also riddled with meteorite impacts, but it also abounds in mountains, canyons, and volcanoes. If it does not contain water, it has an atmosphere contrary to what we could observe on Mercury. This one is very thick and is essentially composed of carbon, sulfur dioxide, nitrogen, and sulfuric acid. The greenhouse effect is therefore very significant. The average temperature is 453 degrees Celsius, or 847 degrees Fahrenheit, a real oven. It takes 7.5 months to make a complete turn around the Sun. Venus has another particularity. It also turns on itself, but in the opposite direction of its neighbors. The planet Mars is composed of a hematite soil. This is what gives it its red color. Hematite is very high in iron oxide. It has many craters, but also ice at the poles, just like Venus. It's interested scientists for several years because of the composition of its atmosphere. It is quite similar to ours since it also contains nitrogen, carbon dioxide, argon, and oxygen. The temperature difference is, however, more significant than on Earth. The highest peaks at only 37 degrees Celsius, or 99 degrees Fahrenheit. The lowest goes down to negative 123 degrees Celsius, or negative 190 degrees Fahrenheit. It is also marked by rather violent winds. Life on Mars is therefore not immediately possible given the climatic conditions. Finally, you should know that Mars has not one, but 2 natural satellites, which are called Phobos and Deimos. The Earth, our dear blue planet, is the only one to date to have such a varied landscape. Mountains, volcanoes, forests, plains, oceans. These specificities and the richness of these landscapes have given birth to many mineral resources, but also organic. It is the only one in the state of current knowledge in any case, which is able to accommodate life. As you know, water is the essential element for any animal or plant life that we know, and on Earth, it is present in all its forms and in sufficient quantity. Our Earth has an atmosphere. It is, contrary to Venus, composed of nitrogen, argon, carbon dioxide, but also of oxygen and water vapor. We can also note temperature differences between the coldest and warmest areas. We find extreme temperatures such as -60 degrees Celsius or -76 degrees Fahrenheit in the poles, up to 45 degrees Celsius or 113 degrees Fahrenheit in the warmest areas. The Earth rotates in 24 hours, which corresponds to 1 day in our calendar system. After 365.25 days, the Earth has made a complete turn on itself. Another important element that differentiates it from other planets is its natural satellite, the Moon. The Moon orbits the Earth and plays a role in the tides. Now, you know a certain number of elements about the universe and the specificities of the different types of planets, but isn't there another question on your mind before we start our descent into the bowels of the Earth? Do you know how our planet was born? Our solar system is, as its name suggests, linked to the Sun. The planets of our system orbit the Sun, but have you ever wondered why? Why do planets revolve around a star? Why aren't they just stable in the middle of the galaxy? Why does the Earth revolve around the Sun and not around another star? Why do all the planets in the solar system orbit the same star? What a mystery, isn't it? Would you like to know the answer to all these questions? Well, hang on. We embark for a few moments into the sky for a little trip in time. It is indeed the appearance of our Sun 4.6 billion years ago that shook up a part of the universe by creating a large cloud of gas and dust, and thus giving birth to our planets. But let's not go too fast and take the time to understand what really happened at that time. The birth of the solar system plays an essential role on the composition of the planets, and therefore of the Earth. This is one of the keys that will allow us to understand the composition of the Earth during our journey. Would you have imagined that you would have to climb so high into the sky to understand what's going on so deep inside the Earth? Incredible, isn't it? The Sun is a gigantic star. It measures about 696,340 kilometers, or almost 433,000 miles. So what happened 4.6 billion years ago in the heavens? How could a phenomenon of such magnitude have come into being? We are going to witness the birth of a star. It is Immanuel Kant and Pierre-Simon de Laplace who in the 18th century developed this idea of solar nebula. Kant, of Prussian nationality, is a great thinker of the 18th century. He's interested in anthropology, philosophy, politics, metaphysics, and cosmology. He's considered one of the founding fathers of the solar nebula theory. It is by combining the knowledge and tools of different disciplines, including astronomy, physics, geology, and planetology, that the hypothesis of the nebula was born. It is still accepted today and allows us to explain and understand many cosmic phenomena, including the formation of stars. According to this hypothesis, stars form in the middle of vast gaseous and dusty regions, called nebulae. These dense clouds also contain molecular hydrogen. Hydrogen is the main component of the Sun and of the vast majority of stars. It's also the source of the energy produced by stars. Thermonuclear fusion of hydrogen is a reaction in which two nuclei come together to create a heavier nucleus. Hydrogen finally constitutes a large part of the interstellar or intergalactic matter. It's part of the composition of the majority of the giant planets, in metallic form, for example at the heart of Jupiter and Saturn, but also in the form of solid, liquid, or gaseous dihydrogen in the outer layers. On Earth, it is found in the form of liquid water, solid, ice, or gaseous water vapor, but it's also found in the emanations of certain volcanoes in other form, commonly called methane. Hydrogen is therefore the basis of our system. Now that you know a little more about this particularly precious material for the universe, let's see what it produces. Now, observe what happens in nebulae. These nebulae of hydrogen gas contain lumps, small grains of dust that wander around in the middle of the gas mixture, much like the little balls of flour in your cake batter. These nebulae are always in motion and gravitationally unstable. This process of gravitational instability, also called Jeans instability in honor of its discoverer, is characterized by an overdensity of matter. The density is more and more significant with each movement because the cloud of gas and dust charged in hydrogen stores then each time a little more matter, the lumps. The solid elements concentrate around a same point. When the density reaches a certain threshold, the internal pressure of the cloud does not counterbalance the external pressure of the cloud. The matter that has amalgamated into small clusters within the cloud falls. These clusters collapse, and in their fall, they form a star. Around this star, a protoplanetary disk appears. Proto means the first. These are therefore the beginnings of a planet. To simplify and clarify things a little, this disk is formed of gas and dust. These are the same disks that will give birth to planets. This is what happened for the Earth and all the other planets that make up the solar system, for example. In this protoplanetary disk, over millions of years in circular movements, a planet can be born. The Sun was born, like the other stars, in a cloud of molecular hydrogen, and then it itself gave birth to our wonderful blue planet. It took a few tens of millions of years for the magic to work and give birth to the planets of our solar system. They are all made of the same material and the same atoms, since they are a result of the same stellar reaction, but as you have seen, they can be very different from each other. The phenomenon takes place 4.5 billion years ago. The disk around the Sun, remember, is made of dust grains. These dust grains on the periphery of the Sun attract each other and eventually agglomerate to form larger and larger stones. This is why the size of the planets can be variable. Mercury is much smaller than Jupiter, for example. But for the Earth to become as we know it today, we had to wait another 500 million years, and some additional phenomena. Our planet is going to meet other bodies, notably asteroids, i.e. celestial objects that gravitate in space, composed of rocks, metals, and ice, and meteorites. When an asteroid enters the atmosphere, it's called a meteor, but when it has resisted heating and disintegration and reaches the ground, it's called a meteorite. The Earth is bombarded from all sides. These impacts with asteroids release a lot of energy and inevitably produce heat, a lot of heat. In its youth, the Earth's temperature was over 2,000 degrees Celsius, or more than 3,630 degrees Fahrenheit. Impressive, no? But that's not all. At that time, the Earth is magmatic. There is no ocean or continents. However, the volcanic activity is very intense on the surface, and the meteorite bombardments continue. The phenomenon then produces gases, and it is these gases that will constitute over time our Earth's atmosphere. Then, gravity forces the heavier elements, such as iron and nickel, to migrate to the center of the Earth, while the lighter elements migrate to the surface to form the mantle. The latter solidifies, as does part of the core. Since the dawn of time, mankind has been trying to unravel the mystery of the universe. Initially, mankind first focused on the Earth, and then extended its field of investigation to the universe. It all began in the 6th century BC. Great names of history and philosophy wandered about the world. Thales, Anaximander, Pythagoras, Plato, and Aristotle tried to understand the mysteries of the environment that surrounds us. Without any scientific tools, we're still far from the latest technological inventions. These philosophers try to determine our place in the world, but also that of the Earth in the universe. They thought that the Earth was round. Aristotle went one step further and explained that the Earth is exclusively composed of earth and surrounded by water, air, and a layer of fire. Contrary to what one might think, even in the Middle Ages, the idea of a flat Earth was a legend. This idea was put forward to prove, once again, the medieval and biblical obscurantism. But in fact, many texts prove the contrary. There is, however, a concept that persists until the 15th century and the arrival of Nicholas Copernicus. Scientific knowledge, but also religious knowledge, then put the Earth at the center of the universe. Everything revolves around it, including the sun. It was Copernicus, a Polish scientist, mathematician, and physicist, who proved the contrary by developing the theory of heliocentrism around 1510. At that time, geocentrism was the law, and his theory was not very well received. It will be very badly received and will even put his own life in danger. To protect himself, he had to admit that it was only a simple hypothesis. It is only many decades later, thanks to the work of Isaac Newton, but also to the technological advances of Galileo, an Italian mathematician, geometer, physicist, and astronomer, that the irrefutable evidence of heliocentrism will be brought to light. On March 12, 1610, Galileo published 500 copies of Sidereus Nuncius, the Celestial Message. It confirms the theory of Copernicus, and the work is quickly sold out. The problem was that the church did not want this theory to be known. He was therefore asked to keep his discoveries quiet. This concept was the object of a religious ban in 1616. The philosopher Giordano Bruno, a follower of Copernicus, was burned in public for heresy. One does not joke with these things at the time. Galileo was also put on trial and decided to recant his thesis in order to not be condemned. Isaac Newton's work put an end to the debate and proved once and for all that the Earth not only revolves around the sun and not the other way around, but that it also turns on itself. For the record, unfortunately, Copernicus never knew that he was right. He died in 1543 in Poland, long before his theory was finally accepted by the world. Copernicus, in spite of his setbacks, allowed the beginning of an astronomical revolution. It was René Descartes who was the first to take a close interest in the subterranean world in 1644. For him, the Earth was an ancient sun. The core, he thought, was a solar matter, and it would be covered by a compact layer of the same matter, then by earth, water, air, and then by earth again. In other words, for him, the Earth is hollow. Kircher seeks in 1665 to explain the volcanic eruptions. These questions lead him to believe that the Earth is indeed an ancient cooled sun, but that it has a central focus connected to the volcanoes of its surface. Finally, Burnet, several decades later in 1681, thought that the globe is a fluid chaos that consists of all the elements and would be ordered by the effect of gravity. The heavy parts go down and the lighter ones go up. Investigations and research continues over the years, but none of them can answer all the questions about the composition of the Earth and its behavior in the universe. In 1749, Buffon, intendant at the King's Garden, proposed a new theory that allowed a great geological advance. He relied on solid arguments that allow him to prove his theories. First of all, he demonstrates with a simple plumb line that the Earth is full. By relying on the features of mountains and the features of the Earth, he establishes through the direction that the plumb line takes next to a mountain that it is weak, and therefore that the Earth is full. Otherwise, the mass of the mountain would be greater than the total mass of the Earth, and the deviation would be greater. Not stupid, the King's Steward, was he? He also argues that the globe melted at the beginning of its history. For that, he explains that the flattened shape of the Earth is inevitably the consequence of a malleable globe, and thus infusion at a moment of its history. He also explains that, since exploration and mining, temperature readings have been taken. The Earth has its own heat. Finally, he specifies that the mountainous rocks are the result of a fusion. In view of these solid arguments, everything leads one to believe that the Earth is full and that a molten center lies at the center of our planet. In the 1800s, a new discipline emerged: geology. This time, we really study the terrain. Cordier, a French geologist and mineralogist, observed a phenomenon that would lead to a new vision of the bowels of the Earth. In the mines, the temperature increases by about 1 degree Celsius every 25 meters, or about 33.8 degrees Fahrenheit every 82 feet. At a depth of 50 kilometers, about 31 miles deep, it appears that the temperature climbs to 16,000 degrees Celsius, or over 2,912 degrees Fahrenheit. At this point, all the rocks are melted. The globe would thus be an enormous molten mass covered by a thin and solid crust, according to Cordier. In the 20th century, new knowledge and technological tools supported the hypotheses of the composition of the Earth. It is at this time that the seismological model appears and allows us to understand some phenomenon, until then unexplained. Shear waves are detected, that is to say, waves that propagate in liquids. This shows that the globe behaves more like a solid elastic body. Several works will be necessary to explain the composition of the Earth, the volcanoes, or the formation of mountains. Following these different studies, Oldham discovered that at a certain depth, the speed of seismic waves decreases. This discontinuity would be established at a depth of 3,800 kilometers, or 2,360 miles. If there are discontinuities, there are inevitably different layers. Mohorovic will highlight the boundary between the crust and the mantle at about 54 kilometers depth, or 35 miles. Gutenberg repositioned the Oldham discontinuity to 2,900 kilometers, or 1,800 miles. Finally, between 1923 and 1952, Adams, Williamson, Bullen, and Birch succeeded in specifying the density of the different layers of the Earth. On the timescale, these revelations are very recent. Only 70 years ago, the different densities of the crust, the upper mantle, the lower mantle, and the core were discovered. Now it is up to you to continue the work of these great names in history. During our trip, you will become a geologist. After discovering the main principles of the universe and understanding how the sun was able to give birth to the Earth, you'll be able to enter our capsule and conquer the depths of the Earth. A geologist studies the characteristics of the inner layers and their interaction with the outer layers of the Earth, such as the atmosphere, hydrosphere, and biosphere. It is a discipline that can encompass many specializations, such as mineralogy, sedimentology, stratigraphy, geochemistry, planetology, volcanology, magmatology, or hydrology. As you can see, the geologist's work is rather complex. However, I perceive in you an adventurous soul and an iron will as solid as the Earth's core. You're ready, I'm sure, to tackle these different themes during our journey. But to understand the mysteries of our planet, we have a lot of work to do, so we need to get started now. Let's start with one thing. What are the different layers of the Earth? In school, you may have been taught the basics. The Earth is composed of 3 main layers: the crust, the mantle, and the core. Each of these layers has its own structure, thickness, and temperature. Its state can be solid, viscous, or liquid. But as a future geologist, you can imagine that you will not stop there. You'll have to roll up your sleeves and dig a little deeper. You'll find that the crust is divided into 2 distinctive layers, just like the mantle and the core. Each of these subparts has its own specificities and a role to play in the life of our planet. Still want to discover the absolutely incredible interior of the Earth? Then take your seat on board, fasten your seatbelts, and let's go. The Earth's crust is the layer visible to man. It is therefore quite naturally that we will begin our journey with it. Vast and extensive, this layer alone seems colossal, yet it constitutes only 2% of the Earth's total volume. We speak of the Earth's crust, but we should say the crusts. Indeed, it's divided into two parts that overlap, the continental crust and the oceanic crust. The continental crust corresponds to the emerged continents and represents 40% of the Earth's surface. It is in a solid state. It is on it that our feet rest most of the time, except when you're at the seaside. The landscapes on the surface of the Earth are rich and varied. We can admire deserts, forests, plains, or mountains. In these landscapes, we can also find fresh or saltwater sources. 4 billion years ago, the temperature of the atmosphere decreased to about 100 degrees Celsius, or more than 212 degrees Fahrenheit. As the Earth's surface cooled significantly, water was able to become liquid and fall from the sky to the ground. At first, the ground was still very hot, so the water evaporated almost instantly. Over the millennia, the Earth cooled more and more. The water was then able to flow into the hollows of the Earth's crust and form pools, lakes, rivers, then the sea and the ocean. I could tell you that the crust is composed of granitic rock and stop on that fact, but I hope that your curiosity is titillating and that you don't want to stop there. Here are some essential points to know about our famous continental crust. If we played geologist and combed through our entire crust, we could find 92 natural chemical elements. While this number may be impressive, in reality, only about 30 of these elements are widely distributed. The others are found in smaller quantities. One of the main elements, 40% of the Earth's crust, is oxygen. You knew it was in the air, but you may not have known that it is also one of the essential components of our soil. The second natural chemical element is silicon. It represents 28% of the crust. Then come aluminum, 8%, iron, 5%, calcium, 3.6%, sodium, 2.8%, potassium 2.6%, and finally magnesium at 2.1%. These 8 major components alone represent 98.5% of the Earth's crust. The other 84 make up the remaining 1.5%, such as carbon, which is 0.048%. In these natural chemical components, we also find the precious metals. The quantity of gold, for example, is estimated at 0.003% of the Earth's crust. Depending on the landscape, the dimension of the crust can vary. Under the plains, it can be from 15 to 30 kilometers, or between 9 and 19 miles. But under the highest mountain ranges, it can exceed 70 kilometers, or more than 43 miles. The density of the Earth's crust is 2.6 grams per centimeters cubed. You're probably wondering why I'm telling you this density measurement. Well, you'll see that it is important in a few minutes. The oceanic crust is the bottom of the oceans. Even though we are underwater, the crust is in a solid state, just like the continental crust. The largest abyss, the deepest trough, is about 10 kilometers, or almost 6 miles. Thus, the thickness of the oceanic crust can be said to be about 10,000 meters, or more than 32,800 feet. On the mainland, it is called granitic rock, but under the ocean, basaltic rock dominates the scene. These are two types of magma at the origin of the Earth's crust. Their composition is quite similar, with some nuances. Basaltic magma contains between 45 and 55% silicon dioxide, while granitic magma contains between 65 and 75%. Then, basaltic magma is also rich in magnesium, iron, and calcium. If the granitic magma also contains some, the quantities of these minerals are much less significant. Another peculiarity is that, with age, the oceanic crust moves like a conveyor belt until it falls into the hot mantle and eventually melts. One could also speak of recycling the layers. There's no such thing as aged oceanic crust. On the other hand, this process does not work for the continental crust, which is why some layers are thousands of years old. It is also important to note that the oceanic crust is much thinner than the continental crust, and yet it is much denser, 3.0 grams per centimeter cubed. This difference in density favors many natural phenomena on and under the Earth's surface. Unlike the continents, the oceanic crust barely floats on the mantle. The natural balance of the two crusts allows a floating on the magma. You now understand the importance of this density variability between the two crusts. This phenomenon brings us to the place of the tectonic plates in the constitution of the Earth. The tectonic plates form the oceanic crust. It is their movements that continuously shape its appearance. There are about 12 main tectonic plates and 40 secondary plates. These plates floating on the magma are nearly 100 kilometers thick, or almost 62 miles. They move a few centimeters per year at a depth of about 2,500 kilometers. If we can establish an average, the plates do not all move at the same rate. The plate located in the Cordillera del Ártico has the lowest rate of speed, less than 2.5 centimeters per year, while the one in the Eastern Pacific, near Easter Island in the South Pacific, 3,400 kilometers west of Chile, has the fastest rate of movement, more than 15 centimeters per year. These movements have given rise to continental drift and modified the landscape of the lithosphere, but they are also responsible for many natural phenomena, including earthquakes. But then, how are such movements possible? The lithosphere, of which the crust is a part, is rigid, but it rests on the asthenosphere, the upper part of the mantle. The latter is said to be ductile, that is to say, that it has a great capacity to deform. Like a rubber band, it can stretch strongly until too much pressure is exerted and causes, of course, the rupture. Here, the phenomenon is quite similar. Mantle failure occurs when a critical defect propagates. This ability to deform allows the Earth to vent its internal heat to the surface. These questions, even for the most experienced geologist, are a real headache. Until a few years ago, scientists had a semblance of an answer. Unfortunately, about 50 years ago, the theory of plate tectonics was abandoned. Since then, the mystery is still alive. But researchers are not giving up and intend to solve the mystery. Recently, between 2018 and 2019, a study was conducted precisely on this phenomenon. The group of scientists made the Earth in a near-perfect model. Their goal, to reproduce 1.5 billion years of evolution of the planet. During 9 months, they developed a supercomputer to get as close as possible to the reality of the evolution of our planet. We're still far from having solved the mystery, but it has nevertheless allowed us to understand a certain number of elements. In particular, they managed to identify the influence of the 2/3 of the surface on the interior of the Earth. Below that, the roles are reversed and the lower part influences the upper part of the Earth's layers. Many studies are still being conducted on the results obtained in this project. It could, for example, explain the birth and death of oceanic ridges, mountain chains under the sea, how subduction is initiated, the phenomenon where the plate passes under another plate of lower density, or explain the appearance of plumes, abnormally hot rocks coming from the Earth mantle. We also know that the evacuation of heat from the core of the Earth to the surface would be responsible for the movement of plates. But we will have the opportunity to study this when we reach the mantle of the Earth. For now, let's continue our study of the oceanic crust. It can reach -2 degrees Celsius in the poles, that is 28.4 degrees Fahrenheit. Below that, salt water turns into ice. At the surface, the sea can reach 32 degrees Celsius, or 89.6 degrees Fahrenheit. But in the depths of the ocean, it can rise much higher, up to 1,000 degrees Celsius, or more than 1,832 degrees Fahrenheit. Unbelievable, you may say? Not so much. The movement of tectonic plates forms what are called hydrothermal vents. When two plates move apart, they create cracks. From these fissures, clouds of boiling seawater and minerals containing sulfur, calcium, and silicon escape. These geysers are not located anywhere in the ocean. They are only found on oceanic ridges, underwater mountain ranges. It is therefore at this precise location that the magma will rise to the surface and form a magma chamber. These chimneys allow the heat stored in the earth to evacuate. The magma is at about 1200 degrees Celsius or 2192 degrees Fahrenheit. It comes out in water at 2 degrees Celsius or 35.6 degrees Fahrenheit. It is the large difference between the two that causes extreme pressure and generates a geyser. Under the ocean, at the point closest to the focus of the hydrothermal vents, the temperature can exceed 1000 degrees Celsius, or more than 1832 degrees Fahrenheit. It is around these famous hydrothermal vents that life could have been born. Now that you know everything there is to know about the two types of terrestrial crusts, you'll be able to board the capsule again to continue your dizzying descent into the depths of the Earth. It is almost invisible, and yet it is there, the Mohorovic discontinuity. This line marks the passage between the crust and the mantle. Once you cross this barrier, you will change universes and discover another hidden part of the Earth, the mantle. The mantle represents nearly 84% of the volume and 65% of the mass of our planet. This layer extends for nearly 2,900 kilometers, or 1,800 miles, and its temperature reaches over 1000 degrees Celsius, or over 2,192 degrees Fahrenheit. So, in your opinion, is the mantle solid, liquid, viscous, or gaseous? What if I told you that there's not one, but two answers to give? Indeed, the mantle is also divisible into two distinct layers, the upper mantle and the lower mantle. Let's take a closer look. The upper mantle extends for about 700 kilometers, or 435 miles. It's located just below the Earth's crust that we just passed through. This part of the mantle is in a solid state, despite temperatures around 1000 degrees Celsius, or 832 degrees Fahrenheit. It is composed mainly of peridotite, rock composed of crystalline elements such as olivine and pyroxenes. This rock is a plastic part, i.e. softer and more malleable. The mantle is made up of basic components, in particular olivine and pyroxenes, but with depth, pressure, but also temperature increases, the rock changes. The minerals evolve and transform. This is called a transition. Indeed, between the upper and lower mantle, there's no clear barrier. The two parts are separated by a transition zone, where the density changes gradually. This feature of the mantle allows convection. This process of heat evacuation is one of the answers to the question of the movement of tectonic plates. But first, let's discover a new layer of the Earth, the lower mantle. Let's continue our descent. Here, everything is different. We're at a depth of about 670 kilometers, or 416 miles. We're entering the phase of gradual transition from the upper to the lower mantle. At this point, due to pressure and temperature, the olivine and pyroxene that make up the mantle will turn into perovskite. This is not a change of structure or matter per se, but rather a change of state. This is the threshold where matter switches from one state to another. In this zone, the rock is no longer quite solid because it enters into fusion. This is what we call magma. The state of the rock is viscous. This zone extends from about 700 to 2100 kilometers, or between 435 and 1300 miles, and the temperature reaches a maximum of 3700 degrees Celsius, or more than 6,692 degrees Fahrenheit. Now that you know the essentials of the Earth's two mantles, I think it's time to talk about convection, don't you think? As you can see, this area of the mantle is particularly unstable. It's animated by convection movements. slow movements, but essential to the Earth. Convection is a way of transmitting heat by circulation of air or liquid. Let me explain. The hot rock is less dense, so it will tend to go up, while the cold rock is denser and will go down. We speak then of upward and downward currents. These movements in the fluid, the hotter parts that rise and the colder ones that descend, define convection. For convection to last over time, it must be maintained. That is, when the hot fluid arrives at the top, it must come into contact with a colder medium, colder rock in our case. The fluid cools down and goes down while hotter fluid replaces it, and so on. These perpetual movements have an impact on the upper layers of the Earth. It is these movements that are partly responsible for the plate tectonics that we mentioned earlier, but perhaps also for volcanoes or earthquakes. This phenomenon is very important for the Earth, despite the sometimes very serious consequences on the surface for humans, animals, and nature. The Earth has significant heat because of its radioactivity, and it must evacuate the stored heat. Before continuing, perhaps you'd like to know why the Earth is radioactive. First of all, we must define what radioactivity is. It is characterized by the emission of radiation by atoms that will fuse or disintegrate. When an atomic nucleus is unstable because it's too light or too heavy, it will fuse with another nucleus or split. It's during these two phenomena that it emits an energy equivalent to the loss of mass generated. This is what is called natural radioactivity. When it is caused by a nuclear reaction, it is called artificial radioactivity. We are all a little radioactive. In the Earth, the main source of heat is radioactivity. Fusion and decay of unstable atoms are very common phenomena in matter. In the bowels of the Earth, fusion and decay are equally common, but fission is one of the main sources of energy and heat. Fusion binds atoms together, decay destroys them, while fission splits an atom into two lighter atoms. Fission heats the magma responsible for volcanism, but also for greenhouse gas emissions. The heat also liquefies the outer layer of the nucleus and favors the movements responsible for the Earth's magnetism. I'll explain this a little later. This magnetism shield is essential for life on Earth. The mantle therefore plays a very important role, even at the surface. However, if this heat production is necessary, it must also be able to be evacuated. To evacuate this heat, there are three possible mechanisms: thermal conduction, convection, and radiative transfer. A large part of the heat is evacuated by the movement of rocks and convection. These currents cause continental drift, but many details such as speed, amplitude, location are still very poorly known. This is why research continues to unravel the mystery of the plates. We will once again go a little deeper into the Earth. We're close to our goal. When we approach the outer core once again, the state of the matter changes to become liquid. It should be noted that the average temperature established over the 2,300 kilometer or 1,425 miles that constitutes the outer core is 3,700 degrees Celsius to 4,000 degrees Celsius, or more than 7,232 degrees Fahrenheit. It is separated from the mantle by the Gutenberg discontinuity at about 2,900 kilometers or 1,800 miles of depth. However, the composition is different from the upper layers. If until now we were dealing with rock, this time the core is mainly composed of iron, 80 to 85%. The other elements that make up the outer core are only guesses. It is indeed quite difficult to determine with precision the lightest elements. Scientists think that it contains about 5% of nickel, and perhaps also sulfur and silicon. The external core being composed mainly of metal, one could believe that it behaves like a magnet. The only problem is that at high temperatures, metals lose their magnetic properties. However, the temperature is close to 4,000 degrees Celsius, or 7,232 degrees Fahrenheit. The Earth's magnetic field cannot therefore be limited to the presence of iron and nickel alone. Another phenomenon is responsible for the magnetic field, and this phenomenon is none other than the dynamo effect. The process by which a rotation is carried out thanks to the movement of convection creates a magnetic field. This is what is called the dynamo effect in astrophysics. Have you ever ridden a bicycle? Well, fine, then imagine a bicycle. See the dynamo lamp rubbing on the back wheel when you pedal? It creates an electric current. This electricity is what turns on the lamp. The process also works the other way. A rotating electric current will produce a magnetic field. Now, let's go back to the center of the Earth. The molten metallic material is in perpetual motion. It is the stirring of the molten iron and nickel fluid that creates a conductive fluid. That is, it produces an electric current. We have just seen that a rotating electric current generates a magnetic field. This is what happens at the outer core. The rotation of the Earth on its axis allows these electric currents to form a magnetic field around it, thanks to the dynamo effect. From the outer core to the center of the inner core, we count about 1,200 kilometers, or 745 miles. Here, we're at the end of our journey. It's quite something, isn't it? We've traveled nearly 6,400 kilometers, or almost 4,000 miles. Would you have imagined for 1 second that such a depth is possible? Do you think that such chemical and geological reactions could take place right there under your feet? Remember, between the lower mantle and the outer core, we went from a solid state to a viscous state, and then finally to a liquid state. Well, as surprising as it may seem, the inner core is solid. That's right. The temperatures of the inner core would be between 3,800 and 55 degrees Celsius, or more than 9,932 degrees Fahrenheit. The pressure due to the heat is very significant. This is why the inner core, which is also called the seed, is in a solid state. The seed would also be in motion, but under the action of the magnetic field, it would turn faster than the rest of the planet. We speak then of differentiated rotation. The galaxy is in motion, just like the sun and the stars. Our planet rotates around itself, but also in orbit around the sun, itself in motion. The convection of fluids also leads to internal movements. Finally, the inner core also rotates, but at a higher speed than the Earth. It's enough to make you dizzy. Now, it's time to go back to the Earth's surface and travel in the opposite direction, the 6,400 kilometers, or 4,000 miles or so, that separate us from the Earth's crust. You can once again enjoy the light and warmth of the sun, the oxygen, and the protection of the atmosphere. Through this journey, we finally understand that all the internal and external layers of the Earth are closely linked. It is the combination of all these layers that allows the Earth to shine with its beauty and to develop life.